So now we're going to look at some more examples of the work energy theorem. In a previous lecture, we looked at cases where the work energy theorem alone can solve problems. But sometimes, as we know, that is not enough. We need to combine both the work energy theorem and Newton's second law in order to solve certain problems. And in other cases, we're dealing with a force that is non-uniform, and we wish to find the work done by non-uniform force in order to apply the work energy theorem. So we're going to look at cases like these. Okay, now our first example involves two famous people, Tarzan and Jane. So the situation is like this. Jane is on one side of the river and Tarzan is on the other side. It turns out that Tarzan was in trouble. So Jane needs to get across the river in order to save Tarzan. But there's a problem. And the problem is the river is infested with alligators. So it's not a good idea for Jane to swim over. Well, fortunately, she noticed there was a vine hanging down from the top of a coconut tree. The vine has length L. So she decides to take this vine and swim over to the other side so she doesn't have to swim in the river. Now the problem is the vine strong enough to support her weight? Well, fortunately, Jane knows enough physics to do this calculation. So she knows the length of the vine, which is L. She knows the angle, theta, when the vine starts swinging. She knows her own mass. And given these parameters, she wishes to find the maximum tension that the vine needs to provide during her swing. Okay, so how does she do that? Well, think about it. Jane starts from this initial position here. Let me label that. The initial position here, initial position. Okay, and she needs to swing over, so she would be doing circular motion during the swing. Right, circular motion. Now, during the circular motion, the tension in the vine will vary, right? But where do you suppose the tension will be the greatest? Well, it's common sense. It'd be at the bottom of the swing, right here. Okay. Reason why it's like this is because in this case, Jane moves the fastest because she's the lowest position, and going the fastest around a circle would require the greatest centripetal force. And at this particular moment, gravity is against it. It's against the direction of the centripetal force because the centripetal force needs to point to the center of the circle, which is here. This is the center of the circle right here. But gravity is actually pointing downwards. So clearly, the most dangerous moment is when she reaches the bottom of the vine. We call this moment F, final moment. Now, going from initial to final moment, the tension of the vine needs to be the greatest at the final point, lowest point of the swing. If she can safely move through that final position, then everything else will be fine for the rest of the swing, right? So clearly, you need to analyze what happens at the bottom of the swing or the final moment. And this calls for the application of Newton's second law because, again, Newton's second law can be used to analyze one moment at a time. Unlike the work energy theorem, which can relate initial and final moments, but it's not about a single moment. So let's apply Newton's second law to the bottom of the swing. To do so, we need to analyze the forces acting on Jane when she is at the bottom of the swing. So we have a tension, right? We have a tension pointing upwards. Okay. That's T. I'm going to draw that. Right? That actually is T maximum, the maximum tension. And at the same time, there's a gravity pointing downwards. Okay, gravity pointing downwards. And that's mg. Now you'll notice that the net force is T maximum minus mg, pointing to the center of the circle, point O. And therefore, we can apply Newton's second law for the circular motion of Jane at that point. We have T maximum. Okay, we'll write that down. T maximum minus mg equals what? Mass times acceleration, right? Mass times acceleration. Now, mass is m. The acceleration, she's doing circular motion, and the acceleration for circular motion is the centripetal acceleration, v squared over r. R is the radius of the swing, which is L, and the speed, we call it v final at this point. So here is, let me draw a v final vector here. V final. That's the final speed. Okay, so if you know v final, then you can find the centripetal acceleration at that point. That's v final squared over r. R is equal to L, the length of the line. So let me v final squared over L. Okay, so that's what happens at the end. We're looking for T maximum, okay? The maximum tension the vine needs to provide. But in order to do so, we need to know what V final is, because we have only one unknown, which is T maximum. So let's find V final. Now, clearly, V final depends on where Jane starts. If she starts from a higher position, when she reaches the bottom of the swing, she will be moving faster. And now she starts from the initial position I, going to the final position F. If we know the initial position, the position of the initial launch point, depending on the angle theta, can we find her final speed? That is, can we relate the initial moment I and the final moment F? Yes, and that will be the job of the work energy theory. Okay, so let's write down the second equation, going from I to F, relating them with the work energy theorem. So during the time, during the sequence when she swings from initial to final, I have W equals delta K, right? W equals delta K, and W is the work done by, let me write that down first. W is the work done by all the forces, right? Going from initial to final. Now, there are two forces present. One is mg, so that's T, that's the W of gravity, and then plus the work done by detention, W of T, right? That's all the work. Equals what? Delta K. Delta K is 1/2 mv final squared minus 1/2 mv initial squared. Now, how much is the work done by gravity? Well, that can be obtained as long as you know how far she dropped vertically, and so that's h. Okay, that's h, and I know what that is. So I can write this as mgh. Right? What is the work done by the tension? Well, here's the thing. The tension varies. We don't know what the magnitude is. We don't know what the direction is, except we know it's pointing towards, from Jane towards the center of the circle, which is point O. Now, so it's radially inward, right? On the other hand, Jane moves tangentially, right? She moves along the arc. So therefore, at every point, the tension is always perpendicular to the direction of motion of Jane. So let me draw a arbitrary moment during her swing. Okay, during her swing. So let's say at this particular moment, she is here. Okay, and then she is moving this way. At that moment, she's moving this way. The tension, so that's V, and the tension goes that way at that moment, right? The tension goes like that, T. And clearly the angle between them is 90 degrees. So therefore, the tension is always perpendicular to the direction of motion, therefore it doesn't deliver any work. Just like we saw, in the case of the normal force being perpendicular to the direction of motion. Okay, so that's very important. We don't have to worry about that. That's zero. That's zero. Okay, the second term is zero. And what does that equal to? That equals delta K, and delta K again is 1/2 mv final squared minus 1/2 v initial squared. Let's say v initial is 0, so she starts out at rest. So that's it, plus 0. So that tells me what v final is. As a matter of fact, you don't have to solve for v final, just for mv final squared, because that's what you need from the first equation. So we have, so then we get mv I get mv final squared equals to, okay, using the last equation, isn't that equal to 2 mgh? Isn't that equal to 2 mgh, right? Now plug that into the first equation, okay? So what do I get? I get T maximum equals what? Move that mg to the other side, so mg plus what? mv squared over L. mv squared is 2 mgh, okay? And then divided by L. So we're almost there, except we have to re-express h in terms of something we know. That's things we know like L and theta. That's easy enough to do. You know, this whole length from O to point F, we know that's L, okay? That's L. And there's a portion of that between here and there, isn't that equal to L cosine theta? That's L cosine theta, right? So what's left is H. So therefore, I know that H equals to L minus L cosine theta. Again, L is this whole length from O to the final point, and then you have to minus the portion between O and this point, okay? And that is L cosine theta. That's why H equals L minus L cosine theta. You plug that in, and you get the final expression for T final. So T maximum. The maximum tension the line needs to provide is mg plus 2 mg, and then h over L. So that's 1 minus cosine theta. Now we clean things up a little bit, and we come up with the final answer. So T maximum equals 2. You can take that mg out. Okay, so that's 3 minus 2 cosine theta. That is our final answer. Okay, so this is the speed. I mean, this is the tension the vine needs to provide at the bottom of the swing in order to support her circular motion. Is that equal to her weight? No, we know it's not the case because the tension must overcome gravity to provide a net force pointing into the center of the circle to support her circular motion, right? So the tension is greater than mg, that's for sure. But how much more? Well, clearly the answer depends on the angle theta. If she swings from a higher angle, from greater angle, she's going to move towards the point, the final point at bottom swings greater final speed, and therefore that would require greater centripetal force, so the tension would increase as the angle theta increases. We can look at some special cases to see if it makes sense, okay? So if theta equals, let's say theta equals 0 degrees. When theta equals 0 degree, you start at the bottom of the swing, right? Do you ever swing at all? No, you're already at the bottom swing, you're not going anywhere. So in that case, you're not moving at all. If you're not moving at all, how much tension do you need? Well, the tension would just be enough to overcome gravity, right? Because the net force, it would be 0. So T maximum should be 0. Is that true? Well, actually, it should be equal to mg, right? Because that's how the net force equals 0. Is that true? Well, indeed, if you plug in cosine theta equal to 0 and cosine theta equals 1, then you get 3 minus 2, which is 1. So then T maximum is equal to, indeed, equal to mg, as expected. Okay, so that makes total sense. We look at some other special case, some other examples. Let's say theta equal to, say, 60 degrees. Okay, I just want to make calculation easier because cosine 60 degrees is 1/2. So if theta equals to 60 degrees, so she starts to swing at this angle of 60 degrees from vertical. That what's T maximum? Well, we can do this calculation now. 3 minus 2 cosine theta is cosine 60 degrees, which is 1/2. So 2 times 1/2 equals 1. You get 3 minus 1, you have 2 mg. That's amazing. That means if she starts swinging at 60 degrees from vertical, by the time she reaches the bottom of the swing, the tension in the swing has to be equal to twice her weight. Twice her weight. Not 20% more, not 30% more. Twice her weight. It's amazing. So it's a good thing that Jen knows physics. So she does the calculation. Otherwise, you know, she might end up with a string that may not be strong enough to support her. Okay, this is a little bit counterintuitive. You might think that, maybe the vine needs to be provide 50% more than her body weight and so on. No, it's more than that if the angle theta is 60 degrees. Even more interesting, let's look at the case when theta equals 90 degrees. Okay, when theta equals 90 degrees, so you start with a horizontal string, a horizontal vine, right? The vine is horizontal, and then when you reach the bottom, what kind of tension would you need then? It's even greater, right? But how much is it? Well, look at that. Cosine 90 degrees, that's 0. So you get 3 mg. Wow. The vine needs to provide 3 times her body weight in that case. It's amazing. Okay, so what did we learn in this problem as far as new technique is concerned? We learned that sometimes it is necessary to analyze a special point, special moment using what? Newton's second law, and that is this equation right here at the bottom of the swing. Okay, at the bottom of the swing. And then in doing so, we find that this is not enough by itself because we have 2 unknowns. What V final we have the tension, and in order to get V final, we have to start with initial position, linking initial and final position using what? The work energy theorem. And the trick to complete that is to realize that tension doesn't do any work. So even though tension is a variable force, we don't have to know what it is, as long as we know it does 0 amount of work. Okay, so you combine the work energy theorem, which is here in the second equation here, with the first one, Newton's second law, you can solve the problem. Okay, so this belongs to a class of problems in which both Newton's second law and the work energy theorem need to be applied to solve a problem. Now, let's look at another example based on the same idea. So you have here a semi-spherical mound of ice. So you have, imagine there's a, it's a hemisphere of ice of radius r. And a person slides from the top of the mound. Now, in this particular illustration, the size of the person is probably a little exaggerated, but when we do the calculation, we can replace the person with a point, and therefore we don't have to worry about which part of the person I should be using to measure for his circular motion. So the person starts from the top of the ice mound. Okay, the top of the ice mound, right here, at 0 initial speed. Okay, and since this amount of ice, he can swing down with slide down with almost no friction, so we don't have to worry about the friction doing negative work. And then as he swings down, slides down, the normal force exerted by the ice mound on him varies in both magnitude and direction, right? What's the question? The question is, you want to know at what angle, okay? At what angle? This is the angle we're talking about. Will that person leave contact with the mound? Okay, so he loses contact with the mound at this angle theta. And want to know what that angle theta equals to. Now, how do you do that? It sounds like a clueless problem to begin with. Well, actually, this problem in terms of method is really just the same as the first problem that we solved, the Jane and Tarzan problem. It has 2 types of equations or 2 types of laws you have to put in. One is Newton's second law applied to a special moment. Secondly is going from the initial point to that special moment as the final point. Now, clearly, the special moment being analyzed is the moment the person leaves the ice mound, right? We need to apply Newton's second law to analyze what happens at this moment. So let's replace the person with a point particle here, a point particle. Okay, so ignore the size of the person, otherwise you wouldn't know what kind of radius you'll be using for the circular motion of the person. The person is doing circular motion up to that point, right? And the circular motion, of course, requires centripetal force. So let's analyze the forces acting on a person. One is gravity, mg. But that's not all. There's also a normal force, right? You would also expect a normal force. right? Pointing radially outwards, normal force M. It's kind of hard to see here. Normal force M. Again, this normal force can change magnitude and change direction. But you have to notice, you have to realize what happens when a person is just about to leave contact with mount. As the person leaves contact, what is the normal force equal to? Well, the normal force is a contact force, right? It takes physical contact in order to have that force. And he's leaving contact, so what's that force equal to? The moment he leaves the contact. That's 0, isn't it? Okay, so you don't have that normal force anymore. Okay, so at the final point, n equals 0. This is something you got to realize. Okay, that leaves only mg. And this angle mg makes with the radius at that point is also theta. mg is solely responsible for the centripetal force needed for circular motion. He is still doing circular motion, but that's the last moment he's doing circular motion. So he still needs a centripetal force. The centripetal force is the net force pointing to the center of the circle, and there's no n anymore. The only force that does the job is a component of mg. What component is that? Well, you just take the radial component of mg. Okay, so you're gonna do this. Take that mg, right? You break it down into this radial component. Okay, here's the radial component right here. So that is the centripetal force responsible for his circular motion. So I can write that down. It is equal to mg cosine theta, right? And mg cosine theta. So mg cosine theta equals what? Mass times his centripetal acceleration. The centripetal acceleration is v final squared over the radius r. V final is the speed of the person at the final moment, right before he leaves the mound. Okay, so this is the result of the analysis of Newton's second law for the person at that special moment, the final moment, F. What are we looking for again? We're looking for the angle theta when that happens, right? See, this is a special moment because n equal to 0. Otherwise, what happens to n in that equation? It will be mg cosine theta minus n, but n is gone, so you only have that. Okay, but in order to find theta, we need to know everything else in that equation, including v final. So how do we find v final? Well, just like we saw in the previous problem, v final depends on where the person starts from. The person starts from the top of the mound, so he drops by distance h, right? He drops by distance h, so that's h. Okay, so linking initial and final, the work done by gravity is mgh. Okay, it's mgh. Right? What is the work done by the normal force? 0. We said that many times because the person moves along the surface of the hemisphere, so he moves tangentially, and the normal force is radial, so the angle between his motion and n is always 90 degrees, so the normal force doesn't do any work. So that is the only work done is by gravity, mgh. And what is that equal to? Equals to the change in kinetic energy. So that is 1/2 mv final squared minus 1/2 mv initial squared. Let's say he starts from rest, that's minus 0. Okay, so we have a pair of equations, just like we saw in the previous problem. The first equation is Newton's second law applied to the final point. The second equation is the work energy theorem relating initial and final points. So all we have to do really is to clean things up a little bit and find theta by eliminating v final. We know that h equals to h equals to r minus r cosine theta, just like we saw in the previous problem. Okay, so let's clean things up a little bit. Okay, so we find mv final squared in the second equation is equal to 2 mgh. So we have mg cosine theta equals to mv final squared over r, so it's 2 mgh over r. Okay, cross of m, the mass doesn't matter because it's powered by gravity anyhow. So it is equal to 2gh over r, but what is h? What is h? H equals r minus r cosine theta. So it's 2g over r times h, which is r minus 1 minus r times 1 minus cosine theta. So cross out r as well, cross out g as well. So what do we have? Well, cosine theta equals 2 minus 2 cosine theta. See, that gives you a unique equation for cosine theta. You can solve that. You get cosine theta equals 2 over 3. Okay, so interestingly enough, I didn't give you any numerical value as input, and yet the output, the angle theta, is a very specific angle. And so what is that angle equal to if you do the inverse cosine? Now, I'm doing that right now. So you do the inverse cosine, and you get the answer to be 48.1 degrees. So theta is a very specific angle, 48.1 degrees. Wow. So at this angle, the person will leave contact with the mount. This problem looks quite different from the first problem. Okay, so scenarios are quite different, and yet if you look beyond the superficial differences, you find that underneath, the methods that we use to solve these two problems are not just similar, they're identical. Again, you analyze the situation with Newton's second law for the special moment, and then you relate the initial moment and that final moment using the work energy theorem. Okay, you can think of a whole bunch of other problems that can be solved in the same manner. Now, let's look at another type of problem. We've so far discussed cases where the work is only done by gravity or the work done is zero. That's relatively simple because gravity is a constant force. But there are situations where the force is non-uniform, okay? And how do we find the work done by that force? Well, a very important example is the force done, is the work done by elastic force of a spring, okay? Now for a spring, if you leave the spring alone, it has a certain length. It's not being compressed or stretched. We call it the natural length of the spring. Now, suppose you stretch the spring by the amount x or compress the spring by the amount x, then the spring will fight back. It doesn't like that, okay? It's going to fight back because the spring doesn't want to change its length. It wants to restore its original length. So the force applied by the spring as you compress or stretch it is called a restoring force because the job of that force is to restore the spring to its original length. The amount of restoring force depends on how far you stretch or compress the spring. Okay, let me draw a little diagram for you. Suppose I choose a coordinate system with x equal to 0 at the natural length of the spring, okay? Natural length of the spring. So here is my x-axis right here. Okay, it starts from here. And when the head of the spring is here, the spring is neither stretched nor compressed, which is at its natural length. And that is when x equals 0. Right? That's when x equals 0 right here. And here is the force of the spring, Fs. Okay, I'm assuming everything happens along the x-axis. So Fs, I'm going to simply use a plus or minus sign to indicate its direction. Positive direction is along the positive x direction, the positive x-axis, and so on. Now, suppose the spring is stretched, so x is positive, okay? Then the spring doesn't like that. It wants to fight back, so the spring gives you a restoring force, which is opposite to positive x, so it's negative x, okay? So the spring now provides a negative force pointing along the negative x direction, and the amount of that force, the magnitude of that force, turns out to be linearly proportional to the distance x. So when you stretch the spring by twice as much, the spring will fight back with twice as much restoring force. You can think of this as an experimental fact known as the so-called Hooke's law, named after the English physicist Robert Hooke. Hooke's law. Okay, so we're looking at what's called linear restoring force. At least for an ideal spring, that's what the situation is. So F is a linear function of x with a negative slope. Why? Because when x is positive, the force is negative, indicating that it wants to pull the spring back to its original length. So I'm going to draw vector. I'm sorry, I'm going to draw a straight line. It's not quite straight, so let me redraw this. I have to do a better job at this. There we go. Okay, so here is an illustration of the restoring force of the spring, and it should pass through the origin right here. When x equal to 0, there is no restoring force. Okay, and the slope is negative. We call it negative k. So we have Fs equals negative k times x. K is a positive number known as the spring constant. Spring constant. It has a unit, SI unit of Newton per meter, because F is in Newton and X is in meters. So therefore K is Newton per meter. You can also use kilograms per second squared, the same thing. And again, this negative sign represents the fact that the job of this force is to restore the spring to its original length. Okay, now given this, what I want to ask is the following. When the spring has been stretched by an amount x, okay, then when the spring pulls the object back to origin when x equals 0, okay, so the object which is tied to the spring originally, the spring is elongated by distance x or stretched by distance x, and as the spring pulls the object back to the x equal to 0, which is otherwise known as the equilibrium position, because that's when the force of the spring is 0, how much work is being done by the spring? Okay, how much work is being done by the spring? Well, the work done by any force, I can always I to F. There's a generic formula for that. Okay, I to F. F dot dr. Dr is the displacement. Okay, now everything happens in one dimension, so I'm going to use the unit vector I to indicate direction. I'm going to start with the final point. The final point is when the spring is stretched by an amount x, not at the origin. The initial, that's the initial position. Okay, the final position is when the spring goes back to the original length, the natural length of x equal to 0. Now F is actually Fs in this case. Fs in this case. It is along the negative x direction, so I can write this as negative kxi. Okay, I is a unit vector along the positive x direction, and then dot dr. What's dr equal to? Well, dr is not equal to dxi, right? I mean, dx is positive if the length of the spring increases, and dx is negative if the length of the spring decreases. In our case, it actually decreases. Okay, so we can finish this integral now. Easy enough to do. You have I dot I, which is 1, right? I dot I, which is 1. And there's a negative k as a constant. We take that out, negative k. Integral from 0, x equal to 0 to, I'm sorry, from x equals x to x equal to 0. All right. And then x squared, the x dx, when you integrate over, you get x squared. And what is that? What is that equal to? Well, there's an overall negative sign here, but don't forget the integral itself is also negative because you integrate from x back to 0. So the answer for the integral is negative 1/2 kx squared. Actually, negative 1/2 x squared, and don't forget there's a negative k sticking out. So overall, it's positive 1/2 kx squared. Okay, that is the work done by the spring as it tries to, as it pulls back this mass from a stretch position to the final equilibrium position when x equal to 0. The reason why this work is positive is not just the math. Okay, it makes sense because the force points along the negative direction, x direction, and the movement is also along the negative x direction. So this block is being pulled by the spring. So therefore, it gets faster and faster. Okay, so the work done is positive in this case. Now, as the block tries to move outwards from equilibrium position, the spring will do negative work because the spring tries to hold it back. It doesn't want it to move away from equilibrium. Okay, so that is how an example how you calculate the work done by a spring. All right. With this knowledge in in mind, we can now look at a problem involving a spring. So here is our last sample problem for this lecture. This problem has its own value because we're dealing with a variable force, the force of the spring, along with a uniform force, which is the force of gravity. Okay, so we can see how we mix things together. We have a block of mass m. Initially, it is positioned at distance h above a platform here, this massless board, this massless platform here. Okay, this board, underneath that board, we have a spring, ideal spring of spring constant k. Okay, and since this board is massless, it doesn't compress the spring at all. The spring is at its natural length. Okay, we can call this x equal to 0. So let me establish a coordinate system starting from this position, going, say, downwards. That's x equal to 0. Okay. Now, once you drop this box from rest at distance h above the springboard, it's going to move towards the springboard while accelerated by gravity. It will hit the springboard with a certain speed. We know how to calculate that speed. It's very easy. It's the square root of 2gh. Everybody knows that by heart now, right? What happens next? That's what's more interesting. Once it starts to hit the spring gets compressed. Therefore, the spring fights back with a force. Now, initially, that force is not very big because you have barely compressed the spring. Remember, the amount of restoring force from the spring depends on how far you compress it. The more you compress it, the greater the restoring force. Initially, you have a tiny amount of compression, so the spring force is very little, even though it's still upwards. It's against the direction of motion. So you get a upward force from the spring, but it's very small. In the meantime, you still have gravity, which is downwards. So overall, the force is still positive, right? I mean, still downwards, which means positive in our designation, right? So that means the block will continue to accelerate even after it starts to compress the spring, because the overall force is downwards. But that overall force is no longer just mg. It is mg minus kx, isn't it? Mg doesn't change, but x increases. So at some point, so this force will decrease and decrease and decrease, but it stays downwards as long as mg is greater than kx. Okay, so the block continues to accelerate, except at a slower rate. It doesn't slow down, but it accelerates with smaller and smaller downward acceleration. Now, at some point, it has reached an acceleration of 0. That's when the force equals 0. Okay, that's called equilibrium position. That's the point where the net force on the block is 0. After that, does that block immediately stop? Well, this is the point where the force equals 0. Does that mean the velocity also equals 0? No. When force equals 0, what's also 0? Acceleration, because F equals ma. F is 0, A is 0. When acceleration is 0, does that mean the velocity equals 0? No. Acceleration is how fast velocity changes. When acceleration equals 0, that means velocity has reached what? Either a maximum or a minimum. In this case, it's clearly a maximum, because before that point, the velocity kept on increasing, okay? Kept on increasing. So the velocity actually reaches maximum at that moment of equilibrium. And after that, because it has a velocity, in fact, the largest velocity, it's not going to slow down immediately, because that would take an infinite acceleration to do that. Cannot do that. So it will continue to move downwards, but this time the net force becomes upward, which means the block finally starts to slow down, until at some point it is temporarily stopped. Okay, so we want to know a couple of things. We want to know how far does it go downwards before it reaches the block, before the block reaches maximum speed, and what is that maximum speed equal to? Okay, so the block starts from here. It's going to reach this point. It's going to reach this point with V maximum. Okay, I want to know what this distance equals to. This distance, we call it A. And secondly, the block will continue to go downwards until it stops. Somewhere down there, it stops. Now I want to know how far it goes down even further. We call this distance A prime, okay? So I want to know A and A prime. I also want to know V maximum, okay? Those are things we want to know. Now, this problem is not suitable with Newton's second law, at least as far as our experience is concerned, because once the block hits the spring, then the net force on the block is no longer uniform because the force of the spring depends on how much is compressed. So you're dealing with a non-uniform force leading to a non-uniform acceleration. I mean, we can do it if we really have to, but if there's a way we can avoid dealing with non-uniform force, we'll take that. And it turns out we don't have to use Newton's second law to analyze this problem. We can simply use the work energy theory. Okay, there are two forces doing work. One is mg, and the other is the force of the spring, elastic restoring force. We just have to find the total work done, and then equals the change in kinetic energy. We can do that. Okay, now so let's begin to solve this problem. Part A of the problem. Okay, I want to know what A equals to. What A equals to. What's A again? A is how far the block has to go downwards, has to compress the spring when it reaches the greatest speed. And we know the force, once it hits the springboard, we know that the force equals to, using downward as positive, okay? The force on the block equals to mg minus kx, right? Mg is downward, which means positive, minus kx. Okay, the force of the spring is upward, so it's negative, right? And again, it's greater than 0 if mg is less than, is more than kx. And it is less than 0 if mg is less than kx. Now, greater than 0, because downward is positive. So when a force is greater than 0, that means the force is downwards, which means the block continues to be accelerated. Okay, and so the block initially gets accelerated, and then it starts to get decelerated. At a turning point is when the net force becomes 0, from down positive to 0, and then to negative. So when the net force is 0, that is when it starts from acceleration to a deceleration. So A is, the compression equals A when the net force equals 0. So set the net force equals 0, okay? And that is when mg equals kx. That x is A by definition. That is the amount of compression which will give you the greatest speed according to analysis. This analysis is not based on the work energy theory. It's based on Newton's second law. Okay, so we found A to be equal to mg over k. This, in fact, is the so-called equilibrium position because the net force is equal to 0. Again, before that point is reached, the force is always downwards, therefore keeping the acceleration downwards so the thing gets faster and faster. After that point, the force becomes negative or upwards, so the thing starts to decelerate. That's why at this moment, the speed is the greatest. Okay, now how, and the next problem, how far you have to keep on going downwards so that at some point it stops. So what is A prime equal to? Well, this problem, you think about it, this part is actually harder than point A, because in going from V maximum to V equal to 0, it is facing a upward force which is non-uniform, right? X changes. So if you want to use F equals ma to solve this problem, you're dealing with non-uniform acceleration. I mean, you can integrate to find the velocity as a function of time, and you can set the velocity equal to 0. That's doable, but it's not something you want to mess with unless you don't have a better choice, because you're dealing with a non-uniform force. Do we have a better way to do that? And the answer is yes, we do. Again, we resort to a different approach to work energy theorem. Okay, so let's see how we can do that. The work energy theorem says the total work done by all the forces equal to what? The change in the kinetic energy. Okay, so the thing starts out from a distance h above the springboard. So by the time it reaches the springboard, it already has a speed. But where do you choose as the initial point? Where do you choose as the final point? Well, to make the situation more general, let's start from initial point where the block is dropped. We call this initial point. At a final point, let me choose an arbitrary location. An arbitrary location, okay? This location right here. It's too thick. Arbitrary location, say here. It's x. So starting from the initial point to the final point where where the spring has been compressed by an amount x. This is x. At that point, I want to find the speed. Okay, then we can see where the speed is the maximum, where the speed is 0, whatever you want. Okay, so from initial to final, I have delta k equals w. Okay, so w equals delta k initial to final equals delta k. How much is the work done by gravity, initial to final? Well, the distance dropped from the initial position is actually h plus x. Don't forget that, okay? So the work done by gravity is positive, it's mg h plus x, right? And next, what is the work done by the spring force? If the spring gets compressed by an amount x, well, is that work positive or negative? It's negative, because as the block goes downwards, the force of spring is upwards. It tries to slow the thing down, right? So therefore, the work done is negative. And how much is that work? It's negative 1/2 k x squared. We saw in the previous example it was positive 1/2 k x squared. That's when the block is being pulled by the spring, gets faster and faster. Here, the block is being slowed down by the spring. So that's why it's negative 1/2 k x squared. Okay, now what does that equal to? That equals delta k. Delta k is k final minus k initial. K final is 1/2 mv squared. Okay, 1/2 mv squared. I'm not writing very well with this pen today. Hold on. That's v final minus v initial, which is 0, because the block starts from rest. So this is the equation that tells me the velocity v of the block at any moment, okay, after it compresses the spring by an amount x. Now, with this, I can solve for both parts a and b. Okay, I can solve for both parts a and b. I can find what a is, I can find what a prime is, and I can also find v maximal. I didn't really find v maximal in part A, did I? I only found the magnitude of the amount of compression, big A, right? So let's start from here and let's find all the answers we're looking for. Okay, so how do you find the moment where you have the greatest speed? Well, the speed is a function of x, the amount of compression, right? I'm looking for a special value of x such that speed v is a maximal. So all we have to do is set dv dx equal to 0. So in order to find, so let's see if we can get the same result. Okay, find v maximum. Okay, find v maximum. Find a and v maximum. We can do both. Okay, you want to set dv dx equal to 0. So this is a particular location x such that v is maximized. All right, so let's do that. Let's take this equation, highlighted equation, and let's take a derivative, time derivative of every term, not time derivative actually, d dx. Okay, let's take d dx for every term. Let's do that. The first term, mgh, the derivative is 0. The next term is mgx. The derivative is just mg. So just mg, the first term. Okay, and you have, that's, we're talking about here, okay? And then after that, you have negative 1/2 kx squared. You take a derivative, what do you get? You get kx. And there's a g here, sorry. Kx, right? Kx. And what is that equal to? Equals to, okay, d dx of 1/2 mv squared. So you have 1/2 m, then you have 2v. 2v dv dx, right? Chain rule. But wait a second, what is dv dx? Isn't that equal to 0? Right? Because we want to find the location where where v is a maximum, so dv dx is equal to 0. So that tells me that mg minus kx has to equal to 0. And therefore, x equals 2. mg over k. That x is a special value, it's actually a. That a is the amount of compression when you have a maximum speed. And that's exactly what we got right here. Okay, the same expression, same result. See that? Same result, mg over k. Okay, so that reproduces the same answer. But what is v maximum equal to? Well, simple. You already know what x is, where v is a maximum. So plugging the value of x right here, this x right here, into what? Into this equation here, and look for v maximum. So let's do that. Okay, so then I have mg. You have mg h plus x. X is mg over k. Right? That's x. And then minus 1/2 kx squared. So minus 1/2 kx squared. X again is mg over k. You square that. What is that equal to? That equals 1/2 mv squared. It's not just any v, it's v maximum. Okay, from that, you can easily find the value of v maximum. All right, I'm going to leave that as exercise for you to figure out, clean up the left-hand side of the equation, but you can easily find that, not a problem at all. Okay, so that answers v maximum right here. So we used the work energy theorem. And if you don't do that, if you use Newton's second law, I mean, the only thing you can easily find is the magnitude of the capital A, the amount of compression for maximum speed. But the actual value of the maximum speed is not something easy to obtain because you're dealing with a variable force from the spring. And second, let's find A prime. How far do you have to go further down? That actually is also a piece of cake because all we have to do is set v equal to 0. Because as it goes further down by distance A prime, you find that v becomes 0. So just set v equal to 0. Okay, so set v equal to 0. In order to find the amount of compression which will eventually stop the block from going further down. So you have mg h plus x minus 1/2 k x squared equals 0, okay? And that x is the amount of compression upon which the block stops. So that x is what? Is a plus a prime. According to the drawing that we have here, it goes down by distance a first, and then it goes down by distance a prime. So the total amount of compression is a plus a prime, and that is where v equals 0. So you can easily, this is quadratic equation for x. You can easily find that, find x, and you can find a prime because you already know what a is. Okay, so that's how we solve this problem. Again, this is a case where Newton's second law is not the best method to take because you're dealing with a variable force. But if you use the work energy theorem, you just have to consider the work done by all these forces, and we can easily find the answers to the problem. So we again in this lecture look at some examples, some more complicated examples involving the work energy theorem, and you can hopefully see the power of this theorem at work. So in the next lecture, we're going to talk about a concept related to work, and that is the concept of power. And after that, this chapter will be done.